Continuing from the last video on Galilean transformation, today I am going to start with Newtonian relativity. Do not be worried about the fancy term. This is same the concept of relative velocity which we study in class 11 and 12. So we have to get the transformation for velocity and also for acceleration. So let us begin with the same Galilean transformation. X prime is equal to x minus vt. So as we know that uh, velocity is nothing but the derivative of distance with respect to time, so dx by dt. Similarly, acceleration is derivative of change in velocity in with change in time, so dv by dt. So I can do this simple transformation. So if I differentiate with respect to t or t prime, it doesn't matter because t is equal to t prime here always. So dx by dt minus, remember velocity is constant, so v differentiation of t is 1. So now this I can since t is equal to t prime, dt is equal to dt prime, so I could simply write it as dx prime by dt prime is equal to dx by dt minus v. Since we are taking only one coordinate system, like we assume that only the frame of reference is moving with velocity v, s prime is moving with velocity, this is s prime and this is s, this is moving with velocity, constant velocity v with respect to s, only in x direction. So let me write this as ux prime is equal to ux minus v. So this is the transformation along x direction. So similarly, we can get the transformations in x, y and z, like uy is equal to u prime y is equal to uy and uz prime is equal to uz, because those components are not changing. So similarly, I could go into the transformation which we have for the velocity. That is, if I generalize along all the three directions, u prime is equal to uh, let me write this, u prime is equal to u minus v. V is a constant, so remember this. So this is a more general case, and this is what is the concept of relative velocity which we know. This is concept of relative velocity which we studied in Newtonian mechanics. So now let us take an example. Consider that an electron, two electrons are ejected in opposite directions from some radioactive atoms in a sample of radioactive material at rest in laboratory. This is electron 1, electron 2 are coming at each other, or you can say that uh, opposite directions, so they are going away from each other. So this is more better one. So what is speed? So if speed of each electron as observed by laboratory observer is 0.67 c, then we have to know what is the speed of one electron as measured from other. So this is simple problem which might seem it like this is the same as like two trains are moving opposite to each other in the same direction, starting from same point. So what is the velocity of the train as observed by the passenger? So here, what is the velocity of electron as observed by it? So this, if we add by simply adding it, since they are in opposite direction, I will simply add it, we may get 1.34 c. This is wrong, because we know that highest the speed highest speed is c, like we cannot go more than c. in the speeds are not greater than c in nature. So this is what so we have to find what is wrong here, right? So now we will again obtain the acceleration transformation for acceleration. uh, this is going to be, again we have to differentiate the velocity transformation. Like if we take only x component, ux prime is equal to ux minus v is a constant velocity. So now if I differentiate with respect to time again, dt prime is equal to differentiation of ux with respect to minus v. So this is nothing but I can simply again write it as same thing only. So t prime and t I will exchange, and so ax prime is equal to ax. So this is, acceleration doesn't change in inertial since the velocity is constant. The frame of reference s prime is moving with constant velocity. So our constant or uniform relative velocity. So we can see that this is a conclusion that the acceleration of particle is unaffected by the uniform relative velocity of the reference frames. It applies to v in arbitrary direction as long as v is constant. So what is v is constant? So now if I take v is equal to three directions like I cap plus 2 j cap plus 3 k cap. This is one such constant velocity vector. But if I take some a variable varying with x like sin x, I cap, or other values, then it is not. Then this is not a constant velocity as this varies with x. So now one more conclusion is that acceleration will change if it is not constant unless and until. But one more thing is we are always dealing with constant velocity frames because this is we are considering that inertial systems. We are only considering inertial systems. So now this is that one more thing we can conclude from is that some quantities which remain same for all inertial observers is termed as invariant to inertial frames. So some quantities will remain same for all inertial observers. That is, see here acceleration is same. Acceleration is same. So for all inertial observers. So irrespective of reference frame. So here one such is acceleration. So Newton's laws of motion, I can conclude by saying three things: that Newton's laws of motion are invariant for all inertial observers. So this is one important point. And then also like inertial observers will, as you know from Newton's law, they will agree with whether momentum is conserved or not. Momentum conservation or not. So they will agree that other values of may be different like velocities and different things, but they will agree that whether the momentum is conserved or not. And then third point is that the numbers like it may vary for different inertial observers, but laws of mechanics, this one laws of mechanics will be same in all inertial systems. So these laws are applicable and also same in all inertial systems. So these are the conclusions which we can get from Newtonian relativity. So now let us move to the introduction to special theory of relativity. The two I will discuss about the two postulates proposed by Einstein about special relativity when he published a paper. So that I will continue in the next video. Thank you. Keep watching.